engineer. I've been working in various places around the world. I'm based in the UK now, and I'm particularly interested in how we can make the agricultural process more efficient. And because I'm an engineer, then I look obviously at the engineering solutions. I've been developing precision farming along with a whole group of other people for the last 20 years. But as I have looked at how technology can help crop production, I have then looked at engineering to be able then to move how far can we go, what are the limits, what can technology enable us to do in the future that we can't do now. And so that's why my talk about agricultural robots is tied in with precision farming, because in some respects it tends to be the ultimate form of precision farming, where we can actually then get the machines to do many of the simple tasks, and in some cases not so simple tasks, automatically for us. But I should say also that I like to consider myself as being a systems thinker, a systems person. It's all very well developing, say, a new robot or a particular machine, but unless you understand the context of it, unless you can understand a way of engineering so that the context and the solution work hand in hand, then it's unlikely that we would have a successful product or a successful machine. And so therefore, I like to consider these things in terms of systems. Okay, so that's my preamble of where I'm coming from in the past. This is the university that I work for now. Just started here just over a year ago. As Marcel says, I'm head of engineering here. We've got 300 engineering students. We offer two unique courses in the UK. We're the only department of agriculture engineering in the UK now. And we have two courses, one in agriculture engineering at undergraduate level and off-road engineering. But we are very applied, like all other agricultural engineers, and because we teach practical aspects of engineering, our students get employed very quickly. So 98% of students are employed within 6 months of graduation, which is a good record. And we're going to be starting a new master's in precision farming in 2013. Okay, so again, just a little bit of background. Before I started here, I was project manager of the European Future Farm project, where we were looking at how technology can be integrated together to be able to come up with a better system, a more practical system, and one of the aspects we were looking at was robotics. And so we had the field robot event, or we did try and support the field robot event, and you can see a selection of the different robots that came together to see what they could do in practical agriculture and horticulture. Okay, so if we then try to look forward, obviously one of the things that we often do is to look backwards first. And if we look at the way what people perceived agriculture to be many years ago, I mean, we think we're pretty clever people now, coming up with automatic steering and driver assist. But of course, there isn't anything new under the sun really. So the earliest automatic steering system I could find is from 1885. But it's interesting as people considered what agricultural machinery would become in the future, and often it was in terms of industrial type farming. And that's where we're dealing with large areas and big machines, and often very efficient machines as well. But it's often in terms of modifying the environment to suit the machines. But I think that we are now at the stage where we should be able to develop smart enough machines to be able to go out into the natural or the semi-natural environment and be able to deal with those situations, so that they should be able to sense themselves, sense their environment, and be able to change their behavior according to the context within which they find themselves. So I see the way that I tend to think of it is that we should really try to make the machines smart enough to be able to deal with the semi-natural environment, not laser plane all the fields and have them huge areas and all totally flat and so on, but make the machines do what we want them to do. We've seen equipment getting bigger all the time. Current mechanization is very efficient. The amount of time that a tractor or an operator spends per hectare is getting lower all the time. This is the economies of scale. That's the main reason why tractors are getting bigger all the time, to take use of or make use of economies of scale. But if we then think about the sort of tractors and equipment that we see on farms today, are they going to be twice the size in 10 years' time? Are they going to be 10 times the size? Well, I think most of us will probably say the answer is definitely not. So how can mechanization be improved in the future? And to me, the obvious way is that it's going to be a lot smarter. And in the meantime, it's going to be smarter on manned machines, and eventually it's then going to be smart enough to become autonomous. And so therefore, what we're talking of at the moment is a system, as we're developing it in the universities, that will be smaller and smarter. I know that Timo's got an exception because he's got a great big tractor that he's robotizing at the moment. But until we know more about the what is safety and what is reliability, I think the smaller machines will move ahead quicker. And when we understand these things, understand what is needed for reliability and safety, it can then scale up to any size machine. So the main driver that made me think about coming back into robotics was the concept of management units. Now, in traditional agriculture, perhaps farmers will apply the same rate across the whole field. So if they apply fertilizer or seed density, it will be the same rate all across the field. We saw with precision farming that where we're getting variability in soil types, variability in yields, that it makes sense to divide the field up with virtual boundaries to be able then to have variable dose rates or patch application. And we then suddenly realized, well, if it should be better, if we get more control over smaller areas, how small can we go? Well, certainly what we've seen from research is that we can go right the way down to single plant care, plant level husbandry, or as our Japanese friends call it, phytotechnology, plant level technology. But of course, if it's a manned machine, it doesn't make sense to treat individual plants necessarily, because often it might take too long to treat each individual plant. So there are sort of compromises here. The autonomous machines are capable of treating each individual plant, but in some respects it's often limited by our scale of management. If we have an on-the-go system that can measure an individual plant and treat an individual plant, then I think we can have full automation. But if it requires management decisions to be able to decide should we put more on or less on in this patch, then the size of treatment is then the management unit, and that will often be significantly bigger than an individual plant. So I think we're starting to see the limitations to which these treatment regimes can go down to. And as I say, we do have the possibility of going right the way down to individual plant scale autonomy. I mentioned that I like to take a systems approach to these machines, and in fact what we did a few years ago was to realize that modern systems, modern agriculture, there's a lot of pressures on farmers. Particularly we found all this out in Future Farm. There's new laws coming on, clean water directives, changes in world prices, the economics, and environment issues and so on. And that's on one side. So these are all pressures off the farm coming onto the farm for the manager to deal with. And then we've got all of the agronomic requirements as well of being able to grow the crops that you want. And so in some respects what we did was to start with a clean piece of paper and then say, well, if we've got this wonderful range of opportunities from technology that can go right the way through to robotics, can we come up with a complete new system? Now, I'm not saying that that system has been developed, but we are currently, obviously as a group, this group, are thinking about how this system should or could develop. But it needs to be able to understand the interaction between the machines and what the roles of the machines are to be able to come up with a system that does work efficiently and flawlessly. So develop a new generation of machinery based on the plant needs, not on the machine needs, which is what we do at the moment. It allows us to do operations we cannot do now or find too expensive or time consuming. Low energy. The one common factor with a lot of the work that I think that we do is to reduce energy, and particularly when we're dealing with these smart machines, to be able to get or develop intelligently targeted inputs. We'll be seeing a number of examples later on where if we know what is happening in the crop canopy, there are ways in which we can only put on the minimum amount of energy. When I'm talking of energy in this context, I'm talking of whether it's diesel, fertilizer, pesticides, whatever, cultivation. These are all energy inputs, and if we understand a little bit more about or can sense what is happening locally, we can fine-tune the energy inputs to only put the minimum amount that is needed there to create the environment that we want. We can come down to small area or plant scale operations. Compaction is an issue. I'll deal with that in a moment. Modular and scalable, rather than having just one big machine with a fixed work rate. It's possible if we had a fleet of these machines that could then we can add another one in or take one out. We can scale it up and scale it down. There's a lot of advantages from having a much smaller, more flexible work system than perhaps just the one-off big machines that we have at the moment. Cost effective. I think that the robots that we're now developing can be made from, most of them can be made from existing available components. If you think about what the big tractor manufacturers have to do, John Deere, CNH, Massey Ferguson, whatever, they have to make specific back axles, specific gearboxes, specific, maybe not engines, but there's a lot of investment having to go in for small numbers. But with the sort of robots that we're visualizing now, I'm sure they can be made from mass-produced parts that already exist. And then if we do have a system, it has to be able to deal with fleet management, which of course is what we're also discussing in terms of manned machines as well. So to be able to come up with a system as we're designing it, I decided to use a classic systems approach by looking at agricultural robotics from different perspectives. So we had a brainstorm in Greece to try and work out what these perspectives would be. I'm not saying this is all of them, but it seems to stand the test of time. Obviously safety, so we need to look at agricultural robots from a safety perspective, energy, economics, environment, management, mechanization, technology, and society. And if, as we develop the system one by one, we can systematically look at our designs from each of these perspectives and make sure that all of those requirements are then met, then we're much more likely to have a robust system that is more likely to be successful. And so the trouble is that that becomes very complex very quickly, and we can go out a few more layers with that again. But this is something that we have to do if we are going to come up with a system to be able to carry out these tasks. And in fact, I think a lot of the principles that we've got do adhere to the requirements from many of these perspectives. So I don't see any real issues with these. So I think the sort of things that we're working on are meeting the requirements from these perspectives. Okay, as I mentioned before, energy. So if we just look at the whole farm as a system, where does energy come from? It all comes from the sun. It comes then directly or indirectly to the farm through light, air, rain, sunshine, and so on. But of course, in prehistory, all this energy was then stored in fossil fuels, and we use those fossil fuels to this day for chemicals to go onto the farm. That energy also comes through in terms of fossil fuels for machinery and fuel, which gives us a fairly energy-intensive input to the agricultural process. And the output then, of course, is the foodstuffs that we then sell or eat. But we've also then got issues of pollution, waste, and biomass. And of course, we've seen recently a lot of interest in energy crops, and we've then been considering can we have closed-loop systems, energetic autonomy on the farm. And when we thought of this, we thought, well, great, we can grow energy crops on the farm and fuel the tractor. This is going to be really good. But it reminds us once again that there's very little new underneath the sun, because that's what farmers used to do 100 years ago with their horses. So instead of a tractor, they would have a horse, and the horse would eat the grass off the field, and so there was an energetic autonomy system there many years ago. But what we're trying to do now is to look at intelligent placement, and so to be able to reduce the amount of energy coming into agriculture. Excuse me a minute. Excuse me, I've got a bit of a dry throat. Reduce or intelligent placement will then give us a reduction in terms of the energy going into the system, and be able then to reduce the wastes and the off-farm pollution and things that we don't want. So that brings us to robotic agriculture, which I am trying to develop the concept of it being multiple small intelligent machines that in certain niches can replace large man tractors, multiple machines to increase work rates, longer working hours, safe and reliable, easy to manage. Developing this concept of a robot shepherd a little bit more. For many years, when I was trying to develop robots, I was trying to take people out of the system and to get the machine to work entirely by itself, and I realized that that's an absolute fallacy. Whatever we develop, people are still inside the system. They may not be sitting on the machine as they do with the tractors at the moment, but the person is in terms of the system, very close to the machine, because the person is responsible for the machine, and the machine is doing what the person wants to do. And so the concept of a robot shepherd might now be that you might have multiple robots working in the field, and the person then might be overseeing these machines, or at least being in continual contact with these machines whilst they're doing other things. And so in many respects now we need to reinvent mechanization to give smarter machines that can care for these individual plants. Lightweight, small, autonomous. One of the things that we're often trying to develop, and it is a genuine challenge, is computational autonomy. What I mean by that is that we've got all of the hydraulics, electronics, mechanical arrangements. We can have legged robots, wheeled robots. We can all sorts of good engineers can produce these things for us. But can we come up with a system, a computational system that is autonomous, meaning that it can cope with all of the situations that's then thrown at it? And of course it requires a lot of perception, a lot of sensors, a lot of understanding of the context. And in some respects this is the hardest part of agricultural robots, or in fact of any type of robot, is in terms of how do we put enough smarts into the machine to get it to do what we want it to do in an automatic way. Some groups are, particularly at Bristol Robotics Laboratory, developing concepts of energetic autonomy, meaning that, again, a little bit like the closed-loop system, there are some robots that are running on sugar at the moment, and in fact, would you believe, on dead flies, and there is a biodigester that is actually working on slugs. There is a robot that can go out and recognize these little things that eat the lettuce plants and can put them into a biodigester and get energy from them. But these are highly inefficient and they're not practical, but they have been demonstrated. The concepts of weather independence and the weather dependence at the moment, perhaps the agronomists want to be able to put seeds into the ground in Northern Europe in the springtime, but because the tractors are so big and so heavy and the soil is so weak, that the tractors do not go out into the field because they would damage the soil. They'd sink into the soil and cause a lot of compaction. And so in some respects the current machinery system is limiting what the agronomists actually want to do. And if we can come up with a smaller, smarter machine that doesn't weigh so much, then we may be able to put the seeds into the ground when the farmers want them to go into the ground. That's the concept of weather independence. Now the concept of weather dependence, maybe a machine is, or at the moment if a tractor is going out and wanting to spray the crop and the wind gets up and the driver will then stop, or maybe probably even go home and start again next morning because the wind is too much. But if we've got a robot that's out there that's got its own weather station on it, then when the wind gets up the robot can stop, and then when the wind drops half an hour later the robot can start again. So the robot is adaptable and can then do what is needed according to the local conditions. We've got the concept of redundant system architecture. Normally as engineers we don't like redundancy, but I feel that it's actually important and actually should be designed into the system so that if one part of the system fails, then we've got an alternative. And this is a way of being able to make sure that we do have the ability to understand ourselves, the robot can understand itself, or to be able to, in the next line, deal with graceful degradation. So instead of having a catastrophic failure where all the lights go out and it sits there and we can't see anything, it's all just shut off, that the machine should have self-awareness within it to be able to tell us that a tyre is flat or an engine is overheating, or that there is a particular problem with a particular subsystem. So the concept of normality and self-awareness is an important part of, I think, a smart machine. I've got there identifiable behaviours, and this is my approach to how we then design what the machine does. And I'll leave that for another presentation. But it is effectively the concept of identifiable behaviours and the ability to switch between behaviours. But we need to be able to understand the context to be able to do that. And it should be able to work at night and so on. So there's a whole range of different requirements and opportunities. Okay, I'm realizing that I'm going on a little bit, so I'll try and move a little bit faster. The machine behaviors, behavior-based automation, navigation, route following, obstacle mapping, useful task, refueling, refilling, these are all of the behaviors. And to be able to change the behaviors due to a particular trigger and a context. But we need to be able to have a system that can cope between deterministic and reactive behaviors. And if we wanted, I know intelligence is overused, but it's like the Turing test, as indistinguishable from human behavior. So if the robot's out in the field doing weeds and it's behaving in the way that you or I would do it, then we could consider it to be useful to us or on the verge of intelligence. So the behaviors themselves are divided into two tasks, purely deterministic and purely reactive tasks. The deterministic task can be determined beforehand, so if we know that we've got a field and we know the machine and the working width of the field, we can plan out a route where that should go. The reactive tasks are those that react to unknown situations with predefined behaviors. So they don't need to recognize every system, but they only need to be able to recognize the class of the problem. So if we've got an unknown object in the field that becomes an obstacle, if it's dynamic, then we wait for the obstacle to get out of the way, and if it's static, then the robot would go around it. But we wouldn't necessarily have to identify what that obstacle was, but just as it is an obstacle, and then we need to react to it suitably. And of course then, as I say, a hybrid system is the best one of all, where we can then have the ability to be able to have both types in there, because the manager will want to optimize what the robot will do in the field, or the tractor does in the field, before it goes there, but it must also be able to deal with reactive situations. Okay, so the deterministic route planning, where get an optimal route plan to follow beforehand. Again, Timo's an expert in this area with the field segmentation. But there are other techniques here as well in terms of skip rows and alternate ways of planning what the machine will do. Particularly what we do at the moment is craft knowledge, where we just choose the longest line, straight edge down a field, and then most of the operation is done in parallel to that. But many of the other fields become a lot more complex than that, and it's not so intuitive. So we do need to find ways of optimizing this. In Future Farm we had a go at doing this. If you'll find a website, web-farming.com, you can log into this site, and it's got it's a mashup with Google Earth, and you can then go anywhere in the world and click on the outline of a field and tell it what sort of tractor or model that you're going to use and the working with, and it will come up with, well, it's the first version of an optimal route plan. We need to do some more work. It's a work in progress, and if anybody has got some good algorithms that they'd like to use with us, I'd be happy to incorporate it within the system. But to me, this is the next logical operation beyond the current A/B lines that tractors are using, that will move directly across into full route planning. So if we move on to phytotechnology, the concept where we are designing a system that does not have the current constraints that we have with existing machines, but we've then got the ability to design what we want according to crop needs. It falls into three main areas: establishment of the crop care, and then selective harvesting. So I'm going to go through some examples of these. Now, I mentioned before that compaction is a significant issue on many farms. This crop that we see here is sugar beet, and we can see a compacted layer underneath here where the roots cannot get through, and that compaction is caused by the tractors. The reason the compaction does not occur above that layer is that is the plough layer. So every year the farmers will plough that up and cultivate that. But when we look at this in terms of the energy, up to 90% of the energy going into cultivation is there to repair the damage caused by the machinery in the first place. Now that's ridiculous, meaning that we're out there moving around with these big tractors, and the reason that we're out there moving around with the big tractors is that we have to have a big tractor to be able to rip up the compaction, and the trouble is that the big tractors have caused the compaction in the first place. So we've got a real catch-22 situation there. So It's important for this system not to cause compaction in the first place, in which case we don't then need to be able to have the big machines to rip it out. We're developing new terminology in this area, particularly when we're talking about the plants and the seeds. So we've been developing the concept of a seed map. Now I'll show you an example of how we can automatically produce a seed map. That's where we can then get the geographic coordinates of every seed that goes into the ground. So with the RTK GPS that gives us 2 centimetre, we can do this relatively easily. The next concept is a crop map or an emergent map. So not every seed will produce a plant, and sometimes the plants will come up in different places from where the seed is. But we can use this information later on when we come to the weeding system. We've then got the concept of the weed map, where we've got weeds being scattered maybe in a random manner or in patches over the field. The crop is established in lines, but the weed is then established in a more random way. We then have the inter-row area between the rows and the intra-row area, which is then between the plants within the row. And then the final concept is the close to crop area. Now this is important, particularly when we start coming to mechanical weeding, because we have to take extra care if we're putting a machine into this area, because we don't want to damage the plant canopy, and we don't want to damage the root zone. So here's the seed mapping system that we developed in Denmark. It's a standard high precision seeding system, but what this has got an RTK GPS on here and some electronics with some light beams underneath each of the seed shoots, and every time the seed drops down through the shoot, it breaks the beam and we can record the position. We create a quadrat out on the field with a camera over the top looking down, and we can then georectify the image on top of the seed positions, and we can then usually find out that the seed or the actual seedling emerges within 2 centimetres, which is what the GPS is rated at. But of course we have to bear in mind that we could put the seed into one position, and through the aggregate sizes and other reasons the plant can actually emerge. So the whole thing is sort of normally within a couple of centimetres we can know where the plants will be. One of the issues that we've been dealing with is this whole thing of mechanization in terms of agronomy making life simpler for the machine. And if you've ever wondered why do we grow crops in rows, well, of course the reason for it is that it makes it easier to develop a machine. Right from the first days of cultivation, where the caveman was out in the field dragging a bent stick behind him, creating a furrow and putting seeds into the ground, then that was a very simple machine, and we don't need to be limited by that anymore. And what each plant needs is equal space and equal access to resources in that space. But in fact what we've actually then finding is that we're still getting rows, but in a different direction now. And so it brings us to the concept of what we really want to have is some type of grid seeding. But again, there's nothing particularly new in this, because they did that with horses, again, more than a century ago. But if we can come up with ways of being able to get robots to move around and come up with, or even manned machines, come back to the concepts of synchronized planting, then we are optimizing the area for each plant. And if we then get the weeds developing in here in a random manner, we've then got the ability to be able to go through orthogonal inter-row weeding, which then doesn't need any intelligence at all, just follows the up and down the rows, but then can be able to take out all of the weeds. Now I'm going to start showing some videos. There should be a video running in the lower right hand corner. I tried it out with Marcel yesterday and it might be a little bit jerky for you, in which case I apologise. but you can see here one of the first runs of our autonomous tractor with a side shift toolbar. So there's two toolbars there, one fixed to the tractor, one with a side shift. And that's got the second GPS on it. And so they're both trying to steer to the same route plan. So the tractor is moving up and down the field and wobbling from left to right, and the side shift toolbar is then adjusting itself to take out the fine errors. Here we can see, again from Denmark, the autonomous crop scouting systems that we were looking at. The robot in the top left-hand corner is the ATRV Junior from iRobot. That's effectively a sensing platform, and with a bit of luck you should see in the bottom left a video that was stitched together using mosaicing, where it was able to be identify not only each individual seedling but also the growing point of each seedling. That work was done by Leah Tang, who's now in Illinois. Iowa. Sorry. And he did this work as I think part of his PhD. But that's a very useful bit of information for us to be able then to use later on. Here you can see the crop scouting robot. The API platform again was done in Denmark. Again, essentially a mobile instrumentation platform. Now I can see the video running in the background, but it hasn't come forward. Okay, I apologize for that. There was a video of it running. In Japan, a lot of work's going on smart machines. This video was taken from a few years ago, but we can see a broadleaf weed sprayer with cameras underneath the black plastic, and where it identifies the weeds, then will only spray the weeds, only spray the broadleaf weeds. And, I think they were saving 50–60% of the weeds of the spray at that time. What has been developed again in Denmark has been the weed recognition system, where we can use active shape recognition. I think we've managed to get up to 26 different species of weeds, and if we then know the weed, and we then know the species, and we then know the leaf area, we can then actually work out the amount of weeds weed killer that was then able to be needed to kill that weed. And I know that work is continuing at Southern Denmark University, and they're doing some very, very interesting work there with microdot spraying. So micro spraying, again, if we got plants and we know where the plants are, and perhaps we've got weeds in the close to crop area, we can then have a machine vision system that can go along and use a micro sprayer that was developed by Dave Slaughter at University of California, Davis, to be able to only apply weed killer just to those areas. And so here we can see it being fitted onto the API robot. We've got some leaves on the ground there, a webcam is looking down, and then we're just through, it's like an inkjet printer, effectively a large inkjet printer, and then just squirting the glyphosate onto that. And we're seeing that we can reduce the recommended dose rate in particular crops from 720 grams per hectare down to 1 gram per hectare. I mean, you know, normally when we're developing these systems, if we can save 5% here, 10% there, well, and again with the microdot system, I know they're now potentially saving 99.99% of the glyphosate needed. So this type of work is going to have a significant impact on what can be done in the future. And some other examples from around the world. We are farming, dealing with farmers, and dealing with muck spreading is a particular task, and so you can see here an autonomous muck spreader that was developed in Sapporo in northern Japan. In organic farming, we use manual labor as ways of extracting weeds. People don't particularly like doing this, and it's then very expensive and it's very demeaning. It's hard work, and so therefore we should be able to come up with better systems. So one system that we used was with to take the cycloid weed hoe from that was developed by Arno Ruckelhausen in Osnabrück, which weeds both the inter-row area and the intra-row area at the same time. And because we know where every plant is, we can withdraw the leg to be able then to avoid the plant. And hopefully in the left-hand corner you can see the weeding system coming through here. So that system worked quite well. It is a little bit of a complex mechanical system, but of course the nice thing is then there's no weed killer needed here, so this is very suitable for organic agriculture. You should be able to see a full screen video now of the autonomous tractor that we developed in Denmark with the side shift toolbar, and then looking down at the cycloid weed hoe. So we're actually coming up with a complete mechanical weeding system here that can run by itself. You can see that the leaves are moving, where probably it's that 2 centimeter error that we're then getting from the GPS, or I guess 4 centimeter if it's plus or minus 2 centimeter where the seed went, and 2 centimeter where the tractor is now going. So sometimes it gets too close, but of course that can be tuned out of the system. Some of this work has been commercialized. There is a company called Garford that is selling a product called RoboCrop. It doesn't use GPS. It's got a machine vision system up on the front that's looking down and can identify each of the plants. This particular one has got a slotted disc underneath it, and it then synchronizes the disc to the plant. And again, you see it's moving the plant, which it shouldn't really do, but I know a later version is using a rotating tine, and that seems to be very successful. Been looking at laser weeding, and so the ability to be able to kill or retard the weeds is an important thing without mechanical or physical method. And we saw before that we were able to see the growing points, and so with the laser we can then just heat it up to between 56 to 94 degrees C, whichever the species is, to rupture the cells and set the plant back. So we can create a weed-free area using lasers, but of course you have problems if you have occlusion. This is the autonomous Christmas tree weeder that we developed. These little plants here are young Christmas trees. It's an important agricultural crop, although they're trees, it's not forestry. And you can see a big patch of weeds here that is growing on top where it's damaging. And okay, there was a little video of that machine, but I'm afraid that doesn't seem to want to work at the moment. But here we've got a side cutter on here, and the robot goes down the row, and the side cutter then cuts all of these weeds, both particularly then in the intra-row area. Again, Southern Denmark University is developing the Hortibot, the spider grass cutter that's then been modified to be able to take a smart sprayer on here, so machine vision is then recognizing where the weeds are and only spraying onto those areas. The Modulaire has been around for many years, and I know I don't know if Timo or any of the other people in Finland are working on this to be able then to put enough smarts into the machine to get it to work by itself. John Deere are probably leading the way in terms of automation and robotic tractors. These have been around for some time now, and I know that maybe Marcel and some of his colleagues there are busy working on these projects as we speak. Again, Japan, Professor Noboru Noguchi is one of the world leaders in this area. I must point out I'm very pleased that he's accepted an invitation. He's going to come to the UK for November, and he's going to be working with us under a Royal Academy of Engineering Distinguished Fellow Scholarship to work with us to develop our new range of machines. So he's got a big project on at the moment as well in terms of looking at a whole range of autonomous farm operations. I've been working with some friends and colleagues in Greece who've been developing the Zeus robot, which some of the two master students developed, and we're continuing to develop that. That will be an instrumentation platform carrying all sorts of, it'll be an RTK GPS with lasers and NDVI cameras. A few years ago I developed a robotic irrigation system. So here we've got a sprinkler system that is emulating a rain gun, so this can be scaled up. As the wind is blowing from right to left, the water is being moved from where it should be towards the left. And if we then have an automatic weather station, we can then adjust the sector angle and the trajectory angle to be able to correct for the wind speed. So we can put the water on exactly where we want the water to go. And the nice thing is that it can have a treatment map then for water, but it can also have a treatment map for a different treatment map for chemigation, because we can adjust different rates of fertilizer, pesticides or other chemicals in there to be able to give us what we want in terms of the chemical application. And the interesting thing about this system was that it could irrigate into corners. Normally these things just go round and round, and you've probably driven underneath them as you go along the road and they squirt your car. With a robotic system like this, can actually irrigate into corners and make sure that it doesn't go outside of where you want it to go. So my particular area of interest is how to develop enough smarts to go into the machine. How do we develop machine intelligence to be able to get these machines to go out and do what we want them to do? So I've been developing SAFAR, System Architecture for Agricultural Robots. I got a research grant a few years back and have developed now the second version of this. It is machine independent and can go onto any machine. The little robot in the bottom left-hand corner, that's the simulation of the Tommy robot, and the full-scale robot is in the laboratory next to my office. And we're also using that on the Zeus robot. And as it is hardware independent and it uses Microsoft Robotics Development Studio, there's a lot of useful tools in there that's allowed us to move ahead very quickly. So in conclusion, equipment's obviously going to get smarter. It's getting smarter in the commercial area. Improved automatic control of well-defined tasks is coming closer all the time. Automated data gathering, better processing into real information, possibility of fully autonomous vehicles. If we can identify the given context, then it won't be such a problem. But the chance to come up with this new system. And here is a vision that I've got of this system that's then based on the best concepts that I've seen from around the world, where we then, I'm not saying that they would look like this, I'm just using this really as a discussion document where we can be able to see or discuss what is actually then going on and come up with new ideas. Now, it's gone very quiet my end. Is anybody still there?
We are still here. Pittsburgh is awake.
Okay. All right. Well, I've just come to the end of this now. So this is the some of the concepts that I would see of agricultural robots. And as I say, I'd be happy to discuss this with you in a question session now, if you wish, and I'd be quite happy to follow up on this at another occasion. So that brings me to the end of my presentation, and if time and energy permits, I'd be quite happy to take questions or enter into a discussion.
Simon, can't thank you enough. This is great.